Hi. So, today we will be talking on a new topic, which is impulse response and arbitrary loading. So, we are done with harmonic loading. Here we will move into other forms of loading. So, let us start with the problem. So, the next topic is impulse load. So, by the name impulse load, we can understand that this kind of loading are a very short duration loading. So, anything that happens suddenly and stays for a very small duration is an impulse load, like a sudden hit by a tool in an aircraft. If there is a sudden bird hit, there is a sudden gust, all this can actually be modeled as an impulse load. So, to summarize, impulse load is nothing but a very small duration load with a certain magnitude. So, impulse load is mathematically usually represented by a Dirac delta function. So, many of you all might be knowing what is a Dirac delta function, but nonetheless we will talk briefly about a Dirac delta function and see how an impulse load can be represented using a Dirac delta function. So, we know that Dirac delta function is a function which is 0 everywhere except at a certain point A. So, we say that del t minus A is a Dirac delta function at A such that it is 0 everywhere except at A. So, it is 0 for all t except t not equal to 1. The other part of the definition of Dirac delta function is that the integral of Dirac delta function over the entire domain, that is minus infinity to plus infinity, is equal to 1, or the area under the Dirac delta curve is equal to 1. So, now an impulse load is the expression for impulse load is given here, which is nothing but an impulse into a Dirac delta function. So, this is an impulse load that is acting at a time instant t equals to a, and it is written as f hat. F hat is nothing but an impulse. It has an unit of Newton into second. It is not essentially force, it is an impulse which is a different parameter and has an unit of Newton second, and that is associated with the Dirac delta function at t equals to a. The Dirac delta function has an unit of inverse of time, that is second inverse. So, this graph shows the pictorial representation of a Dirac delta function. So, we see that, so this blue plot that you see here, this is the Dirac delta function. We see that it is 0 everywhere except at t equals to a. So, this point is t equals to a. So, except at t equals to a, it is 0 all over, and the width of the plot or width of the function, that is the time for which this function acts, which is given as epsilon. Epsilon is very small and almost tends to 0. Okay. So, we say that the duration or the time window for which the impulse load acts is tending towards 0, or the duration is extremely small. On the y axis, therefore, so the total area under the curve is 1, that is given by this expression. So, on the time axis, I have 1 by epsilon, that is the time duration of the load. So, since epsilon is a very small term, since epsilon is tending to 0, this entire thing tends to infinity or a very large number. Okay. So, this is how a Dirac delta function looks. So, an impulse load is nothing but, so an impulse load is nothing but a Dirac delta function amplitude of f hat in the unit is Newton into second. This is how an impulse force is going to look like in time. So, the other point you should remember that this impulse force is acting at t equals to a, that is, this is an impulse load at t equals to a. If we consider an impulse load which is acting at t equals to 0, then the plot is going to look something like this. So, this is going to be f hat into del of t. So, this is the impulse load at t equals to 0. Right. So, let us next see what is going to be the response of a single degree of freedom system when the applied load is an impulse load. So, impulsive response is the response of a system with 0 initial condition. So, we are assuming that it is having a 0 initial condition due to an unit impulse load. Okay, the magnitude of this load is 1 impulse acting at t equals to 0 is called the impulsive response. This is the textbook definition of impulsive response, and the symbol used for impulsive response is Ht. Now, if I write the equation of motion of a simple spring mass damper system, the equation of motion with an impulse load acting at t equals to 0, it can be written in this form. On the right hand side, I have the impulse force, which is nothing but f hat into del t, where del t is the Dirac delta function at t equals to 0. So, given this equation of motion, it has been observed experimentally and also can be derived numerically that the effect of an impulse load acting at t equals to 0 on a system is that it gives the system a single degree of freedom, in this case, and initial velocity u dot 0. So, if I say that in another words, that the effect of this impulse load on this single degree of freedom system is actually imparting an initial velocity whose magnitude is f hat by m. M being the mass of the system. F hat is the is the magnitude of the impulse load, and the initial displacement is 0. So, therefore, the problem of analyzing or finding the solution of a single degree of freedom system because of an applied impulse load is basically obtaining the free vibration solution of the single degree of freedom system with the initial condition of an initial velocity of f hat by m. Okay. So, this whole sentence that has been written here can be summarized as effect of impulse or response due to impulse load is the free vibration of the system with initial condition of u dot 0 is equal to f hat by m. So, we all know the free vibration response of a single degree of freedom. So, let me write down the free vibration response of a single degree of freedom. So, if I have so ut, which is the free vibration response of a S-stop. We have discussed about this in the earlier lecture. So, ut is going to be e to the power minus zeta omega n t into u0 cos omega d t plus u dot 0 plus zeta omega n u0 by omega d into sin omega d into t. So, this has been discussed earlier and we have derived this equation earlier. So, on application of impulse load, applied at t equals to 0, is going to produce this initial condition u0 equals to 0 and u dot 0 is equal to f hat by m, where f hat is the magnitude of the impulse. Now, if I substitute this this initial conditions into this response, we get ut as e to the power minus zeta omega n t. u0 is 0, so this goes to 0, and then I have this also goes to 0. So, then I have f hat by m into omega d into sin omega d t. Okay. So, now this is the response because of an impulse acting at t equal to 0 and with a magnitude of f hat. Therefore, the response due to unit impulse when f hat is equal to 1, due to unit impulse, that is f hat is equal to 1 acting at t equals to 0 or applied at t equals to 0, is going to be h t. As I said before, that h t is the symbol used to represent the unit impulse response or impulsive response. So, h t is going to be f hat is going to be 1. So, it is going to be 1 by m omega d into e to the power minus zeta omega n t into sin omega t. So, this is an important expression and we will keep using this in several parts of the course. So, this is the impulsive response. Of a S-stop. Okay. So, this is the impulsive response when the impulse is applied at t equals to 0. Now, when the impulse is applied at t equals to tau, then the response is nothing but h t minus tau, which is 1 by m omega d e to the power minus zeta omega n t minus tau into sin omega d t minus tau. So, right. So, this is straightforward, that if this is the response of the system because of the impulse applied at t equals to 0, then the response of the same system when the impulse is applied at t equals to tau is going to be this. So, with this we know that what is going to be the response of a damped single degree of freedom system under an impulse load. Now, let us see how we can use this solution. So, this is the final expression. So, this expression is important, and this expression is very important, and we should remain well acquainted with this expression, the expression for impulsive response H t, because this is used for solving a lots of problem, real life problem in vibration and structural dynamics. So, let me move into how this can be further used to derive more complicated problems. So, all this while we have been dealing with harmonic load and then impulse load. Now, what happens, how to solve a single degree of freedom system when the load is completely arbitrary but known. So, this is the example of an arbitrary loading, where the loading is known beforehand. It is of course deterministic, but the variation of the force with time is completely arbitrary. So, here I have drawn it in this way. It could be of any form. It could be something like this. So, any arbitrary load. So, our next problem that we are going to deal with is how to solve a single degree of freedom system when such arbitrary load is acted on the system. So, now let us see that how this arbitrary loading can actually be thought as a summation of several impulse loading. So, what I can do is that I can take a very small slice of this load at t equals to tau. So, what I am doing is that at a time instance t equals to tau, I am taking a very thin slice of the load. Okay. The magnitude of the load at this thin slice is f tau, okay. And the width of this slice, let us say that is del tau, where del tau is very small, it is almost tending to 0, right. So, if I forget about the rest part of the load, and let me also consider a single degree of freedom system with this equation of motion. Okay. So, if I forget about the rest of the load, and if I try to find out the response of this single degree of freedom system for this thin slice of this loading, then my equation of motion can actually be written as f tau into del tau into Dirac delta function of t minus tau. So, what does this implies? this expression of force on the right hand side, that this is an impulse load of magnitude f tau into del tau, which is f hat that I have been talking about. The unit of this is Newton into second, f tau is Newton, del tau is second, and it is acting at t equals to tau. So, I have a Dirac delta function representing this impulse load. Now, I know how to solve this system. The impulsive response of this system for an unit impulse load acting at t equals to tau is h tau, which I know as 1 by m omega d e to the power minus zeta omega n t minus tau into sine omega d t minus tau. So, this is for an unit impulse. So, this is for unit impulse at t equals to tau. Now, if I want to find out the response because of an impulse with this amplitude, this magnitude, then my response u is going to be f hat, that is f tau into del tau by m omega d into e to the power minus zeta omega n t minus tau into sine omega d t minus tau. Right? This is going to be the response of the system. So, let me call this as u tau into t. That is the response of this single degree of freedom system due to this thin slice of the load. Now, we have done this earlier, that for a linear system superposition principle holds, and since this is a linear system, the total response of the system, if I call that as u t, is going to be the summation of all this u tau t. That is, let me explain this in more detail. So, that is, if I take another slice at some another t equals to tau 2, and I can find out u tau 2 t in similar fashion. Therefore, using superposition principle, I can say the total response due to this individual slices of the arbitrary loading. So, I covered the entire arbitrary loading by taking several such slices is nothing but summation of u tau into t. So, which is nothing but summation of f tau into del tau into h t minus tau. So, that is what I have written here. So, this is going to be summation of f tau into del tau into h t minus tau. Now, since del tau is very small and it is tending to 0, this can actually be replaced by a summation over 0 to t, or the time for which I wish to evaluate the integral, evaluate the response, can actually be written as f tau into h t minus tau, and this del tau is going to be replaced by d tau, because del tau is tending to 0. because del tau is tending to 0, this summation can easily be represented by an integral, and this integral is called the convolution integral, and or Duhamel's integral. So, I can summarize this by saying that if I have a single degree of freedom system with 0 initial condition, so let me write down, for a single degree of freedom system with 0 initial condition, we should remember that we started with the condition of 0 initial conditions. Experiencing an arbitrary load f t the response of the system can be written as u t, which is going to be 0 to t f t f tau h t minus tau into d tau, and this is the expression for convolution integral or Duhamel integral. It is called the convolution integral because it evaluates the convolution between the function f tau and h t minus tau. H t minus tau is nothing but the impulsive response of the system when the impulse force is acting at t equals to tau, and the expression of this for a generic case is given as 1 by m omega d into e to the power minus zeta omega n t minus tau into sin omega d t minus tau. So, this expression can be used to evaluate the response of a system or solve for the response of a system under any arbitrary loading condition. So, in the next lecture, we will solve certain example where the convolution integral will be applied to find out the response of a single degree of freedom system undergoing different forms of loading. Thank you.